Hi everyone, I hope this video finds you well. In this video, we're going to be continuing on with section 2.1 and talking about some definitions that apply to square matrices. So we'll go through, discuss these definitions, and also see some examples of them. The first definition is what is a property of a square matrix, which is called the trace. So if A is n by n, then trace of A, well, trace is written TR of A, is equal to A11 plus A22 plus dot 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 plus ANN. So the trace is the sum of the diagonal elements. You should keep in mind here that trace is a property of a matrix. So the trace is just simply a value, and it's found by summing up those diagonal elements. If you want a little bit of fancier notation, you can say that the trace of A is the sum from k equals 1 up to n of a sub kk. And that just is saying that you would do a sub 1, 1, a sub 2, 2, a sub 3, 3, so on and so forth. Just a little bit of sort of summation notation. We will be seeing more of that as we move on. Let's see a quick example. If A is, say, the matrix 2, 0, 3, negative 1, 1, 4, and 0, 0, 5, well, then the trace of A would be calculated by taking those diagonal elements, that 2, that 1, and that 5, and summing those values up. So 2 plus 1 plus 5, which would be 8 here. So the trace of that matrix would be 8. All right. The next three definitions, upper triangular, lower triangular, and diagonal, are things that describe a matrix. So they're not going to be a value, but they're going to be a special type of matrix. So A is upper triangular if A sub ij is equal to 0 when I is greater than j. What that's basically saying is that a matrix is upper triangular if the only non-zero values occur when you are in the sort of upper half of the matrix. In other words, all the values below the diagonal, whenever that row position is larger than the column position, those elements need to be 0 for it to be upper triangular. Let's see an example of that. This would be an upper triangular matrix, something like 2, 3, 4, 0, 5, 0, 0, 0, 1. And what you will notice is that any value that is below the diagonal, in other words, any position that has a larger row position than column position, is 0. This guy right here, that would be 2, 1, and it's 0. This would be 3, 1, and it's 0. And this guy, which would be 3, 2, is also 0, right? That's what this definition right here is actually saying. Those values that are on the diagonal, this guy, and this guy, they can be anything. And the things above the diagonal, those can be anything as well. The only consideration for an upper triangular matrix is that anything below the diagonal must be 0. Lower triangular is going to be identical. So A is lower triangular if Aij equals 0 when I is less than j. And this is just going to be the opposite of an upper triangular matrix. In other words, here, all the values that are non-zero need to live on or below the diagonal. So an example of that would be some matrix like this, something maybe like 2, 0, 0, negative 1, 3, 0, and negative 2, 4, 1. Right, you'll notice here, right, once again, all those sort of positions where the row element is smaller than the column position are going to be 0. So this guy right here, that would be 1, 2, he's 0, 1, 3 is 0, and also 2, 3 is also 0. So again, visually you can see it makes a lower sort of triangular shape there. All right, let's go ahead and take a look at sort of this last definition here. So in this last one, we're going to be talking about diagonal. So A is diagonal if Aij is equal to 0 when I is not equal to j. So a matrix is diagonal if the only non-zero values show up on the diagonal. So an example of this, right, would of course be some matrix that maybe looks like 1, 0, 0, 0, 3, 0, 0, 0, negative 5. And again, for a diagonal matrix, you'll notice that the non-zero values only exist on the diagonal itself. Couple little small notes here, right? We should make a note that diagonal implies upper triangular and lower triangular. So if we were being really spiffy or fancy, we could have just said a diagonal matrix is a matrix that is both upper triangular and lower triangular. That's sort of an awkward definition. It loses the visual nature of it, so we gave this alternate one, but do keep in mind diagonal matrix is necessarily upper triangular and lower triangular. Also do keep in mind that all of these definitions apply to square matrices. So there are extensions of the trace in upper triangular and lower triangular and diagonal that you could use for non-square matrices, but for us, if we talk about the trace or upper triangular, lower triangular, or diagonal, then we are necessarily talking about a square matrix. We're going to continue our discussion of special square matrices with a couple other ones that connect back to that concept we introduced in the last video, which was the transpose. So let's go ahead and take a look at those. So we're going to take a look at two definitions here, what it means for a matrix to be symmetric and what it means to be skew symmetric. So A is symmetric if A transpose is equal to A. So a matrix is said to be symmetric if its transpose is identical to the original matrix. So let's see a quick example of that. That would look like something like A is 1, 3, 0, 3, 5, 2, 0, 2, 6. So how would we check that? Well, you can just confirm that if we did A transpose, remember that the transpose is interchanging the row-column structure. So you would take this first row here and change it into the first column. So the first column would be 1, 3, 0. Then you would take this second row and change that into the second column, 3, 5, 2. And finally, you take this third row and change that into the third column, 0, 2, 6. You'll notice, though, that these matrices are identical, right? They're still the same size, 3 by 3, and all the elements are identical in the identical positions. So since these two are equal, A equals A transpose, this implies A is symmetric. So obviously you can see where the name symmetric comes from. It comes from the fact that the matrix, when you interchange those rows and columns, doesn't change or has that symmetry. Skew symmetric is similar, but a little bit different. So A is skew symmetric if A transpose equals negative A. Now, we haven't formally defined what negative A would mean, but it should be pretty obvious that negative A is going to be the same matrix, just with all negated components. So let's see an example here. Let's consider the matrix A being, say, 0, 1, 2, negative 1, 0, negative 3, negative 2, 3, 0. So let's go ahead and look at the transpose of this matrix. So A transpose here, once again, take that first row, change it into your first column. So that would look like 0, 1, 2. Then take that second row and change it into your second column. So negative 1, 0, negative 3. And finally, take that last row and change it into your last column. So negative 2, 3, 0. Now, clearly, these matrices are not the same. But if we were to build the negative A matrix, negative A would be taking our original matrix and negating all the elements. So it becomes 0, negative 1, negative 2, 1, 0, 3, and 2, negative 3, 0. We'll notice that negative A and A transpose are identical. So that tells us that A transpose equals negative A. A is skew symmetric. So basically, skew symmetry says that there is an element of symmetry, but it requires the negation of all the elements. You'll notice sort of an implication here that since the diagonal elements don't move under transpose, these elements will never move. If they're going to be equivalent in a skew symmetric matrix, well, they don't change position and they have to equal their own negative. That's going to imply that those diagonal elements must be 0. You can think about how you might write out a formal proof of that, and it's something you probably want to try on your own just to get comfortable with some of the notation and ideas here. So symmetric and skew symmetric are very interesting. If you look at the suggested exercises, you'll see that there's a proof that any square matrix can be decomposed into a symmetric and skew symmetric component. That's another sort of interesting proof, and it's something worth trying when you guys get to those suggested exercises. For now, though, we'll wrap up section 2.1 by just having a quick discussion of matrices that are not made up of just real numbers. So let's take a look at that. So we're going to talk briefly about matrix functions. A matrix function, got to switch there. Right? A matrix function is simply a matrix where the elements are functions. So that should be pretty clear. What's an example of that? Well, there's no limitation that a matrix function has to be square, so you might have something like A, and I think that the notation is actually still better to use a sort of soft bracket there, so let's just get that. So you might have something like A of x, which might be a matrix that looks like x squared, 3x, e to the x, 2x, 5, and maybe x cubed, right? So that would be a matrix function, right? Where every element in that matrix is a function of x. Now, of course, you could have matrix functions where all the functions are multivariate or something like that. We're not going to really encounter that, so we'll mostly think about matrix functions of single variables, but that's all a matrix function actually is. Of course, if you were to evaluate it, if you talk about something like A of 2, that would then become sort of a standard matrix where all these elements are evaluated at 2. So it would become 2 squared, 3 times 2, e to the 2, 2 times 2, 5, and 2 cubed. And of course, you could then simplify that into a sort of standard matrix of 4, 6, e squared, 4, 5, and 8, right? And so all we're saying here, matrix function, just matrix where the elements are functions. You treat it just like a normal function, and in the next section we'll talk a bit about doing operations on these. You can differentiate, integrate, and you do that element by element as one would expect. That's going to do it for section 2.1. Our next video will move us into talking about some matrix algebra and working our way through section 2.2.